introduction. Yes. So yeah, I'll continue with explaining a certain picture, which I guess pretty much everything I'll say is a theorem, is a written theorem for T star G mod B or slices, and theorem kind of being written down for quiver varieties. And yeah, I think I started. Actually started. Okay. So yes. So remember, I started a few days ago discussing this refined K equivalence, K implies D conjecture, which starting from a symplectic resolution, we produced, so if x to y was symplectic resolution, then we produced a local system of categories on a parameter space. And so now, well, on a parameter space, but now I can explain in more detail what this space is and connect it to other things that were presented here. So recall from first talk by Andre and talks of Davesh that we have, so we work with the space if V is H2 of X, and well, let's say R to start, and then so then we have a configuration of hyperplanes. Yeah, also this was explained in Sasha's talk, at least. Of hyperplanes, rational hyperplanes. H alpha, and which partition V into cones, and to a cone C, so that to a cone C one can assign xc, this is a resolution, I mean another symplectic resolution together with an identification of H2 of xc with H2 of x.
Does x correspond to some particular cone?
Yes, there is a cone. There is a sort of, yeah, if we sort of, from this perspective, we start with x, then. Yes, and well, so that the classes of ample line bundles for a line bundle L, well, maybe I'll use this notation O of lambda. So lambda is in H2 of xz, or at least more torsion. Well, so is ample for xc if and only if lambda is in C. Okay, so we have this picture, and then we had a more refined picture where we had also
Draw a line. Yes, you can write the
yeah.
Just you draw it too low.
Ah, okay. So we also have, yeah, maybe I'll call this a collection sigma. And so we also have a collection of affine linear hyperplanes. It's a discrete collection. So linear hyperplanes. So it's lambda periodic, and the linear parts line sigma. So again, so picture that appears on the poster is an example of that.
Well, lambda is Equivalence.
Yes. Yes. So. Yes, and so it's equivariant with respect to some symmetries. In particular, it's equivariant, which is lambda equivariant. And so we have
It doesn't understand. Okay, it just x, lambda x on your space.
by translation, yes. And so I just want to say that we have this map, which is V C, well, modular lambda. I mean, equivariant local system is, of course, the same as local system on the quotient. And it maps by the map exp 2 pi I. It maps isomorphically, of course, to a torus that I will call C. And the hyperplanes map to, so sigma tilde maps to a finite collection of codimensional and subtori. So so we have this VC0 maps to something that we can call S0. But then this S has a toric compactification corresponding to the to this collection of hyperplanes, to sigma, toric variety corresponding to sigma. And so this is something that appeared in the talks on quantum cohomology by Devesh. And so if you still remember, so we had this in my first talk. I had this base points of two different kinds, and
So what is this toric variety for T star of G mod B?
well, this is the usual toric variety corresponding to the Weil fan, and closure of a T orbit in G mod B, or it has many other descriptions. So remember we had this, I recall from my first talk, base point. I actually now forget what was the first kind, what was the second kind, but I think it was the second kind. Which was just, again, it's a homotopy fixed point, so it's just a contractible, in this case, convex set. And so it's had the form VR plus IC, where this is one of the cones. And by the exponential map, it maps to a neighborhood x 2 pi I here, since this is a condition on the imaginary part, but applied by I, it becomes a condition on the real part, so exponentiated becomes a condition on the absolute value. So this is a neighborhood of a point of a point. I mean, by the elementary toric variety theory, these cones, they correspond to points, zero-dimensional orbits in the compactification, a neighborhood of a point stratum in S bar. And so I just want to, so maybe we can call this SC. And so I just want to recall that quantum connection, so our remark is that quantum connection as was explained, so it leaves 4xc. It starts its life as a formal series is defined by our formal series near sort of at SC. And and then again is analytically continuous, and so is actually then leaves on S0 with regular singularity on and on the divisors. So from this perspective, it's
So S0 is a regular set?
the complement of subtoric. So from this perspective, it kind of at least heuristically, it kind of matches with the fact that in my sort of local system of more honestly sad representation of this subgroup weight and Poincare group weight, this kind of point would corresponded to just dB Koch of xc.
And is it a theorem that has regular singularities for all x?
I mean, certainly, I don't know if there are general theorems for any. Yeah, exactly. And women.
But there is no theorem for any symplectic resolution it is regular singularities.
No, in that general it's conjecture.
Probably not even known that converges. Probably not.
Yeah, probably even this part before the. Yeah, but again, well, it was written there that things coming from groups and queer varieties, this is certainly a known feature of the known answer.
There are two complementary questions.
Yes.
You can ask about regular singularities given a formula.
No, because the singularities are the.
No, you can ask about this regular singularities near at devices which intersect this point.
It's divided, I'm just
And that is probably.
obvious. No, but there are.
Yeah, no, I know.
Okay, so but now, okay, so recall we want to construct, going back to my sort of linear picture. So recall I promised. A local system of categories. I'm basically just writing down what I said, that VR over VR plus IC. Well, we have dB Koch of XC. And I want to give a little bit more detail on that construction, in particular tell you what sits over Alkovs, or in the historic picture of this pieces in the compact torus. And so now, so Alkovs, they correspond to these non-commutative resolutions. And I want to so construct it via characteristic P quantization. And I want to say a little bit more about this, and because basically many of the ingredients needed here were already covered in Ivan's talks. Okay.
And when you say regular singularities, it means first order poles. Yeah?
That's right. Yeah, not just there. It's not. Okay, so so basically, as Ivan explained, we can construct. Yeah.
Basic question, stupid question, because I wasn't here. So you're saying to a complexified chamber you associate with dB Koch,
Yeah.
but then the Alkov sits inside it.
No. The Alkov is well. The Alkov sits in VR, and this is an open cone. And
I see. So I see.
C does not contain Z.
Yeah.
Yeah, sorry.
But what is true, as I point out, is that any point like that is connected by a canonical path to an Alkov, namely by straight line. Right. So so we can construct. So we have quantizations, so a family of quantizations parameterized by points in lambda. And we have more, but I want to stick to those parameterized by lambda. So O quantum lambda of y, and under some conditions that Ivan explained, it's all global sections of O quantum of x, and lambda is in lambda. And again, for quiver variety, this is O sub stock. And for T star G mod B, this is just essentially the quantizing cotangent bundle is easy. You get differential operators. So this is just differential. The larger D is heavily overused here, and so it's differential operators, but twisted by lambda. So it's, so to say, differential operators acting on sections of the line bundle of lambda. Okay, and so yeah, and O lambda quantum of y is of course just the reduction, central reduction of the enveloping algebra.
You mean gamma of that? Gamma of d lambda?
No, I mean, so where?
X is resolution. Okay.
Yes. Yes. Okay. And so, actually, the key point here is something completely elementary, namely, yeah, key point which is on which this construction hinges is so observation. So for two resolutions, I mean, you have two symplectic resolutions, then they are identified away from codimension 2. So we have and x prime contains u prime, which is isomorphic and have codimension 2, and so everything having to do with global sections works in this parallel way on the two resolutions. So in particular, well, in this way, so you can just say that quantizations for x and x prime are in bijection, so that the global sections match for the two. For matching quantizations are the same. Huh?
So this was an example of what corresponds to the alcove?
No, I'm getting there. Sorry, I'm getting there.
Why? So this O lambda on X corresponded to what?
I'm getting there. So far, I just introduced this object. Just wait. Wait a minute.
The parameters. So I mean, so each resolution of each lambda exists.
At this moment, there is, I mean, at this moment, nothing happened yet. I just introduced some algebras corresponding to lambda. So the next thing I want to say.
You want to say that it's in characteristic 0 still.
Okay, so now what I
want to say that your bijection sends quantization parameterized by lambda to quantization parameterized by lambda.
Yes. That's a good point. So yes, so in a way, this thing was kind of built in my notations because when I write O lambda quantum, then it doesn't refer to x, and are different. Okay, so now I just want to say the following, that so I was kind of didn't make the base field explicit, but what I said so far, and maybe also in the next couple of minutes, applies to all possible characteristics. Yes, and then I'll pass to things specific to characteristic P. And so so we'll say that lambda is good if we have derived localization theorem if R gamma lambda, which is just, well, R gamma from the category of sheaves, derived category of O lambda quantum x to derived category of O lambda quantum of y is an equivalence.
Here formally means for all x.
Yes. Okay. Well, let's say temporary lambda is good for x, but the next, so there is this easy sort of proposition. I mean, that lambda is good if and only if the algebra or lambda quantum of y has finite homological dimension, has finite global dimension. In particular, this shows that this notion is independent on x. What?
No, I mean it's known in many cases in characteristic 0 and maybe in all cases in characteristic P. I don't think it's known in the full generality in characteristic 0.
Okay. And didn't McGurk and Evans prove?
No, they only do Hamiltonian reductions.
Okay, but yeah, that's fine. So it's definitely
So far, y is
huh?
what is y here?
So I started from the setting that x to y is a symplectic resolution.
Okay.
Yeah, and it's clear that yeah, so hence corollary is that goodness is independent. Is x independent? Hmm? Huh?
Since also since good, is such a flexible notion, you can write my goodness.
Yes, that's a good point. And so for obvious point that for a good x, for a good x, sorry, not for good x, but for a good lambda, we get a derived equivalence, derived category of coherent sheaves. Oh, sorry, not yet coherent sheaves, but or quantum lambda of x and derived category of or lambda quantum of x prime. Well, they are both, I mean, they become equivalent because they are both identified with this. So yeah, closing this triangle, we get an equivalence like that. And And so now we get to more non-trivial things. And to proceed further, we actually need to understand. So initially we wanted to work with categories of coherent sheaves, not with this quantized thing. And there is this my kind of favorite trick, and so use characteristic P to pass from modules or quantum of X modules to coherent sheaves, and apologies to people who know me well, but maybe I'll need to spend a few minutes to just say how this works. No, what do you mean? Quantization was constructed uniformly in all the settings we talk about. There is a separate question of how to construct this quantization, and there are also general methods, in particular in my papers with Kaledin, but also in other places. But for these two class of examples, that's completely clear, and I already explained, and Ivan explained how to do this for clear varieties. So far, characteristic P was not important. Yes? No, again, for clear varieties, it's Hamiltonian reduction. For general X, there is abstract theory of quantization. You can classify them. Right. And so the point is that there is this P center phenomenon, which is best illustrated by the case which can be done as an exercise. For K of xd, where K is characteristic P, and so again modulo dx is 1. And so the point is that that this or quantum of X is an Azomaia algebra of rank P to the dimension of X on. So now, sorry, of course, here I am now in characteristic P. And so then this, huh?
You want very much.
Well, for this statement, maybe not necessarily, but yes, soon I will do this on X, and so technically I should write X1, meaning Frobenius twist. So X1 is X times spec K over spec K, where this is Frobenius map. But it's isomorphic to X, so I will maybe be omitting this from notation. And also the class of this Azomaia algebra. Pointed that this Azomaia algebra is splits on formal neighborhood of every fiber of I pi from X to Y. In fact, this is best deduced from from a stronger statement that the class of this, its class in Brouwer group, is a pullback of some class of C, where C lies in Breuer group of Y. So just this last statement for clear varieties was yeah. So this is BMR for T star G mod B. I mean myself, Merkovich and Romanian, and Kobrak and Travkin. For quivers. Yeah, so with this enhancer, if you have split Asum algebra, then modules over this split Asum algebra are the same as coherent sheaves. And let's just, to simplify things, we can sort of replace dB call hex. And this is a technical point, and it's, you can actually do better, but you can work with. So this means that supported on the preimage of this special fiber. And then we get from so for every good lambda, we get an equivalence dB call x dB call x prime. And again, so if we want to do this technical simplification, we can write it this way. So how do we get it? Because using this splitting of Asum algebra, we can identify it with modules, even without D. I mean, we can, maybe I can write it here. Yeah. So we get it from so call of x0 is identified with modules over or quantum of x lambda, and we can put somewhere 0 to indicate the support condition, and same for x prime. And for this quantum guys, we are already constructed this equivalence going through this global sections algebra. Okay, and so finally, to get to the picture we want to investigate the dependence of this on lambda, and that's where all.
So why was it relevant that this is my algebra splits and pulls back from y?
No, again, pulls back from y was not relevant. Because it's just.
Why did you mention it?
No, I'm answering your question. So it's important that it splits, and the fact that it splits follows from this.
And why is it important that it splits?
And it splits because this gives me, for a split Asum algebra, the category of modules is the same as the category of coherent sheaves.
Okay.
In fact, this is relevant somewhat because if I don't want to spend time on this, but if using this, you can improve it and just you can untwist the Asum algebra and work with the whole X, not just with the formal neighborhood of the fiber. Well, there are some technical. I mean, it's more general than quiver varieties. So they work with symplectic resolutions, but there are some technical assumptions about slices to strata, which you can you can look at in the paper. But yeah,
They need to be conical.
That's all.
yeah. Yeah, maybe just to make this a little bit more explicit, let me point out the following. So. By definition, this is the equivalence that I just erased. Just maybe to clarify these things. So all quantum lambda of x. So it sends us shift f to f tensor E, where E is the splitting bundle. And so just a quick example is that if x is t star of something, in particular t star of m, where m is something like g mod p, then E, just on this 0 section, it is the direct image of the corresponding line bundle under Frobenius.
You mean modules over this algebra, right? In the top line. Equivalent.
Yeah, of course. Shifts of modules, yeah. So yeah, and kind of everything hinges on the structure of this bundle, but so some algebraic geometers are interested in the structure of it, and just last year there was a long paper which by Van den Berg and his team, which did it for just GUR to n. I understood this explicitly, but maybe this shows that a very explicit description should not be possible, because then things I'm going to present now would also be explicit. Okay, so yes, so how do I end up with the structure that I want?
So this is difficult to compute even for Grassmannian?
Yes. It's easy to compute for projective space. But again.
Even its class of K theory, in equatorial K theory, that's pretty difficult to compute. Full equatorial K theory.
Okay, maybe. But well, I don't know. It depends on the form of the answer. By fixed points, you can usually do this. But okay, we can discuss this later. So, I mean, maybe just okay. Since we're mentioning this, maybe what will be important for later is that at least if you compute its class in the non-equivalent K theory, then it depends polynomially on lambda, and that will play a role soon. Yeah, and so now we come to a more difficult question of which lambdas are good. And the expected answer, which is known in some cases, is that that's exactly the bad lambdas are exactly this the ones which lie on this hyperplanes. Yeah, but and so maybe let's write it as a claim. And okay, so let me just stick to characteristic P, and then goodness is clearly P periodic. So goodness only depends on lambda mod P. And so the claim is that
What is good then?
The derived localization holds. And so that lambda is good if and only if lambda over p doesn't lie on a hyperplane on H in sigma tilde. So yes, so the status of this is maybe it's less less understood than the statements I was saying so far, and so
No, maybe.
yeah, and
What's written here is not right.
maybe it isn't, but it's almost right. So okay, so
For example, operation of unique algebra like he minus 1 over n is a bad parameter, but it doesn't. What you write is
yeah, so is good for when, yeah, okay, let's put it this way. When lambda over p is not near a hyperplane in and so yes, and so this is definitely known for things like T star G mod B and G mod P, and known for some varieties, and maybe will be known soon for more. And
But isn't it supposed to be reduction of lambda mod p is not in sigma tilde reduced mod p?
no, because
Near to hyperplanes cannot also be bad. This was a remark. Not only points on hyperplane.
so
Near to hyperplane.
okay, let's discuss it later. Okay.
no, I mean in this form it's even more or less proved under some assumption.
What does it mean near?
Well, there is some finite collection of parallel.
It's
The,
same
the linear functional is not less than 10. Okay, for some value of 10. So, and 2 is that the outcome of this construction, so the equivalence. So basically, this says that my construction works when lambda over p is inside the alcove, but sort of deep inside, not near the boundary. And so the equivalence between the category of coherent sheaves, dv cohex to dv coh x prime. I didn't fix a notation for it, but I did expand a construction which involved lambda. So it depends only on the alcove. Only on the alcove in which this lambda over p lies. And so maybe call it phi lambda. So at this point, we already have all the data we need to construct our local system of categories. Of course, we have to check something, but let me maybe briefly say what we need to check. So somehow, yeah, and I said you can do better, but yeah, let's. No, I mean, a more maybe relevant question is what how about characteristic P? But so formally at this point, I only constructed this for field of and here, as Ivan said before, we knew that P is very large, and so here formally I constructed it over fields of such characteristic. But the claim is in particular is that that it lifts to characteristic 0, this structure. The equivalences.
Wouldn't it be enough to show that the reducible, indecomposable pieces of the splitting bundle, they're independent of P?
Yeah, that's right. Maybe even, okay, let's discuss it later. But an equivalences linked to characteristic 0. So, okay, so maybe let's sort of sketch of the proof or idea of the proof. Again, so we have this, maybe the picture is like this. So we have these alcoves, and somewhere on top of this we have these cones. So I have only 2 dimensions. And so basically, kind of our goal was to go from one resolution to another resolution, and then we explained that we can go do it through these alcoves. But to check that these equivalences really combine into a representation of the Poincare groupoid, it's convenient to sort of shift this viewpoint and think that we go from an alcove to another alcove via a commutative resolution. And really what we need to check is that when you go from an alcove to another alcove via some x, well, so you, yes, you can draw such a loop, but you can obtain it by going sort of, by going first to infinity and back. And that's how it's constructed. And the point is that it doesn't matter which direction to infinity you use, provided that this direction in which you travel is ample for the corresponding infinity is just a way to refer to this domain, V plus IC. As I explained, it corresponds to neighborhood of point infinity on the toric variety. Okay, so with this we have our local system of categories, and again, as I explained in the first talk, like the sort of one of the central theorems at this stage is that the corresponding action, I mean, you can without too much trouble add some equivariance here, so you can extend it to, and then that the induced action on K0 is the monodromy of the quantum connection, and to make sense of it, you need to use the periodicity of this monodromy with respect to the equivariant parameters, which is done using shift operators, which Devesh explained. And so, maybe let me say that. So, key theorem is that monodromy of equivariant quantum connection is isomorphic to the induced action and again, to make sense of it, so use shift operators to make sense of it. So, yeah, I'm almost out of time, but so let me start the
5 minutes.
Yeah, okay. So I actually want to, I mean, the next topic is perverse equivalences.
Okay, can I ask a quick question?
Yes.
So you also have, let's say for the simplest one-dimensional case, you have these intervals,
Uh-huh.
and you have points inside and they're all equivalent. And then there is still a, you can make a tensor product with translation by module.
Mhm.
And this is another way to go from.
Yeah, it's
one up.
equivalent. It's
But you have two ways, right? You can go above, you can go below,
Yes.
and then you can tensor with translation by module. How is it related to the?
well, I mean, tensor and translation by module is the same as going through one of these.
As long as it fits examples,
Yes,
it's
exactly.
the same as.
So bimodule is the global sections of something, as Ivan explained in his talks. Global section is bimodule is the global sections of some quantization of line bundle, and there is this compatibility that the line bundle is ample on this resolution.
So shift to the
So
right
there-
is going above,
Exactly.
and shift to the left is going below.
Yes.
Okay.
Okay. So yes, so this is also actually, I mean, closely related to what Ivan discussed in his talk. But so basically, well, we have some a bunch of categories and derived equivalences, and so we basically want to say, just as Ivan did in his talks, that so can and won't say more about well, this sort of half monodromies so by this I mean that we have some Alkov, and we have a neighboring Alkov, and we want to cross from an Alkov to a neighboring Alkov, or we can do something kind of monotrivial, and we can cross from an Alkov to an Alkov symmetric with respect to one of the faces. And if you remember Ivan's doctor, he was in some, I mean, maybe he was working in heuristic zero, but still there was this point that in this closely related context, the derived equivalence of this sort was actually a perverse equivalence. And yeah, maybe I don't have time to explain in detail, but I will say that the so such an equivalence, this is a perverse equivalence, and the part that Ivan didn't explain is that it's governed by central charge. So this is, and this is kind of similar to but different from Bridgeland stability theory, and so this the name for this that we invented is this real variation of stabilities. And this is yeah, this is the way to motivate actually Ettinger's conjecture that Ivan was talking about.
May I suggest an insertion
Yes.
between equivalence and governed? Please put conjecture.
Yeah. I mean, just all of this is again. It is probably for T star G mod B, and for quivers, yes, it hasn't been written down, but
I don't think
it's
they know
close
how
to.
prove it for equivalence.
Maybe for our, it should follow from our paper. Yes, at least. Okay, so should be yes. And for T star G mod B, actually, this is also not exactly trivial, and I think the final step was done in our paper with Ivan from last year. So, yeah, let's just say.
So it's perverse for iteration by dimension of support, right?
Well, here in category OR, but then here in characteristic P we have to support is zero dimensional, but
the
growth of dimension is a polynomial in P. And so but now I'm.
And what is central charge?
Well, that I explained. But this is equivalent to what you just said, but I will explain it next time. And so for T stadium of B,
which is like
no.
residue of the
No, it's not.
In definition of perverse equivalence, defining sheets.
Defining the filtration, yes.
Yeah.
Yes. And so this
is
follows
the
from.
operator on K0, yes? The
From-
central charge.
Say it again?
Is it the operator on K0?
No, sorry. Yeah, it's confusing. No, it's not central charge in the sense of affine algebras. It's central charge in the sense of Bridgeland. So it's not an operator. It's a functional on the K0. So you can say that this central charge is a solution of the trivial limit of the quantum connection. So if you take the quantum connection non-equivariantly, when you kill the equivariance with respect to the dilation operator, then it will be a kind of a boring connection. It will have a flat section, and central charge is basically this flat section. Okay, so maybe I should stop here for today and more time tomorrow.